Let's look at the graph of a potential energy function and see what we can learn by looking in the neighborhood around a specific position. Suppose for the moment we zoom in on location B. And imagine an object released from rest at location B. If the object begins to move and covers a small displacement to the right of delta x, it will also experience a small change in its potential energy, delta U. Let's see if these two quantities are related in some way. Recall the definition of potential energy was that changes in potential energy are equivalent to the opposite of the work done by that conservative force. In the case of a very small displacement, or when the force is constant, we can write the work as the force multiplied by the displacement. A simple rearrangement of this equation shows us that the change in potential energy divided by the displacement is equal to the opposite of the force felt by the object at that location. We can generalize this to any potential energy curve by taking the displacement to be very small. This turns our deltas into differentials, and we get a general relationship between the derivative of the potential energy function and the force experienced by the particle. It says that at any location, if you take the derivative of the blue potential energy curve, make it negative, that will tell you the direction of the force and the magnitude of the force on the object. At location B, a displacement to the right would result in a negative change in potential energy. That means that the slope at B is negative, and therefore the force should be positive, directed to the right. Let's draw that as a red arrow. At other locations near B, the slope is still negative, so the force is still directed towards the right. As the curve becomes flatter between C and D, the force remains positive but decreases in magnitude. At location D, the slope of the potential energy curve is 0, so location D is a location of 0 force. Between D and E, we see a positive slope, so the force would push the object to the left. We can tell that the force at E would be somewhat larger than the force at location F, because the slope at E is steeper than the slope at F. It also appears like location G and location A would be points of 0 force. We have a special name for these locations where there would be 0 net force. They're called points of equilibrium. We use the equations of equilibrium, zero acceleration, quite a lot in our topics on Newton's laws. In terms of potential energy, though, we see that a point of equilibrium is a place where the derivative of the potential energy function is 0. Using our knowledge of calculus, we know that an equilibrium point must also be a location where the potential energy is a maximum or a minimum. Whether the potential energy is a maximum or a minimum can't be determined from the derivative alone. We need to look at whether the potential energy function is concave up or whether it's concave down. If the second derivative of the potential energy function is positive, that means that the function is concave up in that region. If the potential energy function also has a zero derivative at the same location where its second derivative is positive, then we have what we call a point of stable equilibrium. An example on this graph would be location D. Location D is a point of equilibrium, and since the graph is concave up, it's also a point of stable equilibrium. What this means for the motion is that if an object was near D, it would remain near D at all subsequent times, unless it was given more energy from an external source. The motion would be small oscillations around the area of location D. If the second derivative at a point of equilibrium is negative or zero, that means that the point of equilibrium is actually unstable. If we began our object near location G, it might be able to sit there if it was exactly zero force, but if it was anywhere slightly to the left or slightly to the right, the force would be pushing it away from location G, and the motion would become unstable. This is similar to trying to balance a pencil on its edge or on its end. If you set it exactly correctly, it can stay there, but any small deviation away from the perfect equilibrium will result in it falling even farther away over time. We have a relationship between the derivative of the potential energy function with respect to some coordinate component and the force experienced by an object at that location. Let's apply this to some cases where we know the answer, see if it makes sense. In the case of gravity, the potential energy depended only on the y component. It was equal to the mass times the acceleration of gravity times the y coordinate. So our coordinate of interest here is not actually x for gravity, but rather y. This means that we'll be taking the derivative of the potential energy with respect to the y coordinate, and this will give us the y component of the force. The derivative of mgy with respect to y is just mg. The minus sign out front gives us negative mg for the y component of the force. That's interpreted as a vertical downward force of constant magnitude mg. That's what we expect for gravity. However, we also know for gravity that sometimes there can be motion in the x direction as well, even though gravity is present. To generalize our formula to a two-dimensional situation with x and y components, the x component of the force would then be associated with the derivative of potential energy with respect to x. Of course, u does not depend on x, so therefore there is no force in the x direction. Putting these together, we get a force vector for gravity in unit vector notation of minus mg j hat. Let's do another example of a potential energy function that depends on both x and y coordinates. A spring attached at one point to the origin and at the other end to an object. since the object is at some coordinate x, y in a two-dimensional space, the length of the spring is equal to the Pythagorean theorem, x squared plus y squared with a square root. In the formula for the potential energy of the spring, though, this distance, which we call L, is squared. So we get 1/2 k x squared plus y squared. Let's see if this makes sense when we do the derivatives indicated by this formula. The x component of the force due to the spring will be the negative derivative of potential energy with respect to x. Using the power rule, I'll get 1/2 times k times 2x. The y squared term has a derivative of 0 with respect to x. This simplifies to minus kx. For the y component, the derivative plus the negative sign results in minus ky. Therefore, this potential energy function generates a force vector that is minus k x I hat minus k y j hat. In other words, there is a force that is directed always towards the origin that is proportional to k and proportional to the distance from the origin. Use some of the facts we've just uncovered to help us interpret a potential energy function that's given to us. Here we've been given a potential energy function that is equal to 72 over x to the fifth minus 30 divided by x cubed. And these numbers will be in joules and meters to avoid lots of units in our formulas right now. Our first step is to take the derivative of this formula to find out if there are any x values that are stable or unstable equilibria. The chain rule gives us the power rule gives us this for the derivative, and we set that equal to 0 to find x values where the slope is 0. Simplifying this, we'll end up with 360 over x to the sixth must be equal to 90 over x to the fourth. And using a bit of algebra, we can reduce this to x squared must equal 4, or x must equal plus or minus 2. This potential energy function was claimed to only be valid for positive x values, though, so we must choose the positive root x equals 2. This means somewhere at x equals 2, this potential energy function is going to have a flat area. We do not yet know where that is vertically, or if it's going to be concave up or concave down. Let's record this information and do the next step. I've recorded that the point of 0 slope, x sub 0, is equal to 2. Now let's look at the potential energy value at that point. We take the value 2 and plug it in for x in the formula for potential energy. This gives us 72 divided by 32 minus 30 divided by 8. If we subtract these two fractions, we get negative 3/2. For the next step, I need to determine the concavity of the potential energy function at x0 equals 2. Let's take two derivatives of the potential energy function to do this concavity check. Using the power rule twice gives us this somewhat long expression for the second derivative. But we only need to plug in x equals 2 and check the sign of this value. It turns out that this is equal to 5.625, a positive value. That means that at this location, the graph, the potential energy function, is concave up. So we have discovered a point of stable equilibrium at x equals 2. To draw the rest of the graph, we'll only need to consider the limiting behavior of the potential energy as x approaches 0 and as x approaches infinity. We've already found all of the critical points because we've looked at the derivatives. As x approaches 0, both of these terms become very large. The first one becomes very positive, the second one becomes very negative. But because this one involves x to the 5th power, it grows faster, and the overall potential energy will be positive near the origin. This means that the potential energy has a vertical asymptote to positive infinity as x goes to 0. As x approaches infinity, both of these terms go to 0. This one is positive again, and the second one is negative. But again, because this one has a different power than the first, it goes to 0 slower than 1 over x to the 5th. Therefore, the function remains negative as we approach x equals infinity, but it has a horizontal asymptote. Now, what can we tell about the behavior of a system Now let's look at two qualitative conclusions we can make about the behavior of a system governed by this potential energy function. Let's consider an energy level equal to U0. Recall that U0 was -3/2. This is the minimum energy that this system could possess. If the system possesses any energy that is greater than U0, but still less than 0, say E1, the motion will have two turning points, one between 0 and 2, and the other somewhere greater than 2. The coordinate x of the object will oscillate back and forth between these two turning points. Next, let's think of how the system would behave if it had an energy of larger than or equal to 0, represented by E2 here in the red. Motion with this energy value would only have one turning point, somewhere close to the origin. Out to the right, the object would have some leftover kinetic energy equal to E2, because the potential energy goes to 0. So this potential energy function for an object with positive or 0 energy shows a behavior where the object can travel around nearly free at large values of x, but as it comes close to the origin, it speeds up, slows down, turns around, and is accelerated back away. This potential energy curve, and other ones like it, actually do a pretty good job of representing what happens in molecules and compounds. If the coordinate x represents the distance between two atoms in a compound, then when the atoms have a large value of x, they are far apart and basically act like individual objects. When they become close together, there is some preferred separation distance where they have a minimum potential energy. If they are begun with an energy near that, the atoms will stay together and just oscillate back and forth. Finally, if the two atoms have a large separation distance initially, but velocities that will set them on a collision course, the distance between them can decrease, reach a minimum, and then increase forever again. This describes a collision between two atoms that are not bound into a molecule. The dividing point between these behaviors is really described in terms of energy. If the pair of molecules has an energy anywhere below zero, they will remain bound together in a molecule. However, if they're given enough energy so that their total E value is greater than zero, they will become unbound and eventually fly apart as individual objects.